The third law is the law of logarithms of powers. And that law states that if you have a log of x to the exponent n, so a power, base a, you can rewrite it as n times the log of x to the exponent a. So if you take a look at what's happening here, it's taking that exponent and bringing it in front of the logarithm and writing it as a multiplication statement. So again, we'll start with the example and then the proof. So the conditions again are the same. X, y, and a need to be greater than 0, and a cannot equal 1. So for our example, we have the log of 81 base 3. You might be able to solve that directly, actually, without using the law of logarithms for powers, by thinking, to what exponent do I have to raise 3 to get to 81? The answer is 4. But if you can't see that directly, you could apply the law of logarithms for powers to come up with an answer. How could you do that? Well, you could rewrite 81 as a power that you are familiar with. For example, we could rewrite 81 as the log of 9 to the exponent 2 base 3. And the law of logarithms for power states that if you have an exponent inside a logarithm, you can rewrite it as that exponent times the logarithm. So I'm going to rewrite this as 2 times the log of 9 base 3. And you might be able to evaluate now what the log of 9 base 3 is, because what exponent do we have to raise 3 to get 9? The answer is 2. So we could rewrite this as 2 times, instead of log of 9 base 3, the answer is 2, and 2 times 2 is 4. Alternatively, you may have seen that 81 could be written as 3 to the exponent 4, and hence the answer would be 4. But let's apply the law of logarithms for powers and see if we can get the same answer. So we could rewrite that simply as the log of, instead of 81, 3 to the exponent 4. The log has a base of 3. We can bring that exponent in front of the logarithm and rewrite it as 4 times log of 3 base 3. What exponent do we have to raise 3 to get 3? The answer is 1, and 4 times 1 is 4. So there we have it. 2 examples demonstrating how to use the law of logarithms for powers. If you'd like to see the proof is, again, done similarly to the proof of the other two. We're going to use power rules. So we'll start by looking at our right side, and we have n times log of x base a. I'm going to let the log of x base a equal m. And if we rewrite that as a power, that would be a to the exponent m equals x. We need a statement for x to the exponent n. So to get that, we can take x, raise it to the power of n, which means that we would need to take a to the exponent m and raise it to the power of n. And according to our exponent rules, when you have a power of a power, you multiply the exponents. So I'm going to multiply them and get a to the exponent m times n, and that's what x to the exponent n is. If I go back to my left side, we have the log of x to the exponent n equals a. We just wrote an equation for what x to the exponent n equals. X to the exponent n is a to the exponent m times n, and the log had a base of a. Now we have that common property where we have a power inside a logarithm which share the same bases. So we can rewrite this as simply just the exponent, m to the exponent n. I'm going to flip the order here. I'm going to rewrite it as n to the exponent m. In multiplication, order doesn't matter. You can multiply in any order. And what is m? Our initial definition said that m was the log of x base a. So I can rewrite that as n times the log of x base a. And there we've demonstrated that the log of x to the exponent n base a equals n times log of x to the exponent a, which was our law of logarithms for powers.